So hello students, let us begin with continue with our topic with module number 5. In module number 5 we have so far covered ROM array, and today we are going to see SRAM, sense amplifier, and actually decoders we have completed already. So in decoders we have studied na row decoder, various types of column decoder. So these things are already covered before, okay, in ROM array. Alright, in SRAM we will also be studying sense amplifier. So these two topics will be covered. Alright, and also we'll see the difference between SRAM and DRAM. Okay, so these are the topics which we are going to study now today, which is the SRAM, the sense amplifier, decoder we have already covered before, the difference between SRAM and DRAM. Alright, in SRAM we have the following topics. Hello, yeah, tell me. You all do on your own. Now we don't have that much time to cover everything, right? So that is up to you. Okay. So in SRAM, we are going to see its operation, then its design strategy, and its read and write circuit. So these three things which we are going to cover in SRAM. All right. So before starting anything, let us just revise about SRAM. SRAM is static random access memory. It's also called as static read write memory. Static read write memory. Okay. Um, then where do we use SRAM? SRAMs are used in cache memory. So SRAMs are used in cache memories. They're extremely costly, and as you can see clearly, the size of it is also not very high. Okay, here it is 10K size, and the speed is very high in 10 nanoseconds. It's quite expensive also because it's on-chip memory, SRAM. Then we have already seen that static RAM is a kind of a volatile memory. All right. So we are going to see the category of SRAM today, static RAM. Let us also see some memory definitions, memory timing definitions. So see, you have a memory location. You either read from a memory location or you write into it. All right. So let's say we have two read pulses, and between those two read pulses we have a read cycle. So how do we define read cycle? Between the two read pulses, the distance between them is called as a read cycle. Then we have a read access. It takes some time for the memory to give the read access. So when the read access is over, then the data comes. The data is valid after the read access, and then before the next read access starts, the data is valid. So this is the duration at which the data is valid from year to year. Okay, so you have to read within this time. Then we have a write cycle. Write cycle is the distance between the two writes, active high. Okay, initially the write is low, then they are active high. So distance between the two write highs will be the write cycle. And in write cycle also we have a write setup and a write hold. Okay, it will prepare memory, will prepare to write into the memory, that is a write setup, and then the write up hold. So during the write, whenever the read access is over, okay, then the data becomes valid again. And whenever the write cycle is, the write hold is over, then the data is actually written into the memory. All right, so these are some of the timing definitions of read and write cycle into the memory. Okay, because we are going to study SRAM, so we are going to read from the memory data storage and also write into the data storage. Okay, now from here you can write the comparison between SRAM and DRAM. Data volatility, it's yes for both. Refresh operation is no for data static SRAM. There is no refresh operation. The cell structure is basically 60 SRAM cell, and for DRAM it is one transistor, one capacitor. Okay, so you can, I mean, go on comparing. Basically, we will also see its application. DRAM is used in the main memory, and SRAM is used in cache memory or PDAs. Okay, so you can write the comparison between SRAM and DRAM looking at this table. We can compare the writing speeds also, the cost, okay, the power consumption, the cell density. Also, you can mention it. This is just a recap of a memory array. So we have a word line. This is bit line. This is word line. Okay, and the intersection of a bit line and a word line, we have a memory cell. So this is the storage RAM cell. Okay, so to select a particular row, we have to select a particular row address. So it will go to that particular row location. So that is selected by row decoder. And for a column decoder, same thing. We to select a particular column. Let's say the first column, you have to select the column address. Okay, let's say A0. So to select the first column, so it will go to that particular column location, and that column will be selected. Okay, so that's how you select the appropriate word from the memory row. And then there is something called as a sense amplifier. So we will today see what do you mean by sense amplifier and how it is utilized, and also we'll see the read and write circuits. Okay, so these two board blocks we will be exploring it today. I hope I am audible and your slides are visible, everyone. Yes or no? Just a confirmation. Okay. This memory array organization we have seen last time, right? This was used in ROM array. So it's the same as before. We have a row address decoder, column address decoder. We are not discussing much details into it because we are not designing an ROM array or a RAM array. We are going to study SRAM cell. This again a conceptual RAM array organization. Again, it's just similar to the last diagram we have seen. Okay, we have a memory cell. Either it can be a ROM or a RAM. Okay, the common thing is that we have a row decoder. Okay, and we have a column decoder, same as before. And we can select go to a particular column or a row, and then select that particular memory. Only difference is in case of a ROM array, we could only read from the memory, but in case of RAM array, we can read as well as write. So let's go for random access memory or read write memories. So now we'll go for a SRAM general structure. So you can write along with me, or you can just have a wait at just look at the things. All right. So basically, let's start with static RAM. So RAM refers to memory with both read and write capabilities. So it's a memory with both read and write functions. Okay, why it is called as a static? Static means what? It will hold the data, holds data as long as supply or power is applied. That is actually called as SRAM, static RAM, static read write memory. And what do you mean by volatile? Anyone? Volatile memory means what? Cannot hold data if power is removed or switched off. Okay, so it's one and the same thing to static RAMs are volatile memories. All right, so can we start with the basic structure, everyone? So here the memory circuit, I will revise. The memory circuit is said to be static if the stored data can be retained indefinitely, as long as the sufficient power supplied voltage is applied, without the need of external periodic refresh operations. Okay. So let's start with RAM. So basically first we'll start with data storage cell. or we can call it 1 bit SRAM. So it will store 1 bit of information. Okay, so data storage cell in SRAMs, or we can call it 1 bit memory cell. So 1 bit memory cell in SRAM arrays consist of two things. One is a latch circuit, and second is latch circuit with two stable state, with two stable states. Okay, and then it consists of, now let's see how a latch looks like. A latch looks something like this. So you have an inverter. So this is input to inverter number 1. This is output of inverter number 1. Now we have a cross coupled inverters. That means the output of inverter number 1 is given to input of inverter number 2, and the output of inverter number 2 is given as input to inverter number 1. Okay, so this is called as a simple latch. This is a latch circuit with two stable states. Alright, so let's say that the data over here is storing logic 1. So if input to V1, V in 1 is 1, what will be VO1? Hello? 0, right? VO1 will be logic 0. Now if input V in 2 is logic 0, what will be VO2? Logic 1. So this logic 1 and logic 2, logic 1 and logic 0 are the two stable states. Understood? So this is called as a latch, simple latch circuit. So also we can call it as a bistable circuit, which is having a two stable states. Alright. So depending upon the preserved states of the inverter latch circuit, the data has been held into the memory cell, will be interpreted as either as logic 0 or logic 1. Alright. So now we also require two more things. Okay, let me connect my writing pad again. Yeah, the second thing we require is, I hope you are following. Second thing is required is access transistors or access switches to access this memory location. Okay, so this is a cell. It will preserve itself, right? It will go on circulating the same logic again and again. So it will be 1, again it will be 0, it will be 1, it will be 0, unless this is 0 again and this is 1. So it will be keep on keeping it 0 and 1 indefinite period of time. So here it will be 0, 1, 0, 1 all the time. So that's why we have one stable state. So it's a 1 bit memory SRAM cell. Now to access this memory, now this is just a whole state of the memory. It is holding the already existing data. So it will keep on holding, let's say this is Q and this is Q bar or QB. So whatever state the Q holds, that is the memory, it is holding. So Q is stating 0, QB is stating 1, storing 1. So these are the storage nodes. These are called as the storage nodes. So it will keep on storing this same data again and again and again, unless we apply some external voltage over here at these nodes, at Q and QB. Okay, so to access the memory, to read and write into this memory, we require access transistors. So these are called as switches. Okay, so this is drawn like this. All right. So we have two more control signals, which we call it as a bit line and bit line bar, bit line B. All right, and these are your access switches. To access switches can be turned on using word line. Sorry. Access switches will be turned on using, it has a control mechanism using word line. Okay, we have a bit line bar or BLB, and then we have a word line. So what can we use as an access switches? Basically MOS transistors, right? We know MOS transistors can be used as digitally controlled switches. So we will be using NMOS transistors. Okay, so these to access the read and write operation, the data circuit with this 1 bit memory cell, we have to use it using two switches. So whenever these switches are on, then our memory is capable of reading or writing into the, we can write or read from the memory. Okay, and these access switches are turned on using the word line. All right. So we this access switches are controlled by word line. Okay, that will be controlled by following row address selection signal. So that we'll see later. But so far, whatever we have shown over here, is it understood to you? Did you understand this? This is the general structure of a. It's a symbolic representation of a two inverter latch. Any doubt over here? Yes, no, what? Okay. So now next we go for a 60 SRAM cell. Let me directly jump to 60 SRAM cell basics. Okay. So we'll go for 60 SRAM cell basics. Let me start. So basically your 60 SRAM cell has three operating modes. First is hold mode. Next is write mode. And the third is read mode. Alright. Okay. So we'll slowly and steadily build a circuit, but let me just draw the 60 SRAM cell and you know revise it generally. Yeah, six transistor, six transistor. It is made up of six transistors. Okay. So can we start now? Okay. For that perspective, let me give a reference to 1D RAM, one transistor DRAM, dynamic RAM. Okay. So dynamic RAM will have a transistor, let's say M1. Then it has a storage capacitor, which is CL, or a load capacitor. Then here we have a word line and a bit line. So let's say here we have a word line, and on this side we have a bit line. Okay, I'm just explaining the simple structure of a 1T, one transistor DRAM. All right. So let's say when the word is, the word line is activated. So what will happen to M1 when word line becomes 1? Can you tell me? M1 turns on or off? Quickly tell. M1 turns on and it acts as a pass transistor logic. Yes or no? So it will pass the data whatever is stored in BL. So let's say now BL is 1. Bit line is 1. Basically WL is word line and BL is bit line. Okay, it's a memory location. It stores the memory location. So bit line is 1. So what will happen now? Come on, tell me fast. When the bit line is 1, what will happen to this transistor? Come on, I have to cover a lot of topics. So this M1 is storing 1 over, this is logic 1. So this is VDD now. This is also VDD. So this, whenever the BL becomes logic 1, the capacitor will charge. The capacitor will charge via, or M1 charges the capacitor CL. We can say the M1 charges the capacitor CL. So M1 charges CL. So voltage across the capacitor reaches around VDD. Agree? And now if you remove word line, if you make word line equal to 0, what will happen? So M1 has become off. Yes or no? So M1 has become off. Can the capacitor discharge now? Can you tell me? Is M1 is off? M1 is off means this is open circuit, right? So there is no discharge part for CL. Yes or no? So CL will hold that charge. This is what you call as non-volatile. The data is not destroyed. So data is not destroyed even when the supply is removed. So this is the basic working of a 1-bit dynamic RAM. Of course, we say that there is no discharge part when, but this transistor can be weak on, and some leakage current can flow, and then the the charges across this capacitor can slightly discharge. Okay, but in reality, in general situation, in ideal situation, if this transistor is off, the capacitor will hold the data, and that's the basic working of a dynamic RAM. Got it? This is a working of a 1T dynamic RAM. Now let's go back to your SRAM cell. Now this is your SRAM cell. Can I start with the operation? The working. Are you all ready now? So it has 3 states: hold, write, and read. Can we start with the working, everyone? Okay. Now you can draw along with me. So remember, it consists of 2 inverters. So how it was? Just like this, 2 inverters. Yes or no? 2 cross coupled inverters. So this is V in 1, this is VO1, output of 1, this is V in 2, this is VO2. So this is inverter number 1, this is inverter number 2, and we have to exactly draw that. So please draw the inverters. Draw the inverters in this manner. This is VDD, this is ground. Okay, let me call this as transistor M1, transistor M2, transistor M3, transistor M4. Understood this? This is inverter number 1, this is inverter number 2. Now where is inverter number 1? This is inverter number 1. Inverter number 1 input is this, right? Inverter number 1 input. So output of inverter number 1 is connected to input of inverter number 2. So this wire, this is output, right? This is output of inverter number 1 is connected to input of inverter number 2. See, this way. Do you agree? Yes. And output of inverter number 2, this is output of inverter number 2, is connected to input of inverter number 1, like this. See, wherever I am drawing the dot, that is where the connection is. Okay. So these 2 nodes are called as storage nodes. So this node, we call it Q. So this is a storage node. It stores the data logic over here. Similarly over here, we have QB or Q bar. We can write QB. So this is again a storage node. Okay. These are storage nodes. Q and QB. Alright. So can I explain the operation now? Yes or no? So let's say, are you all, we are explaining hold operation. So what will happen in hold operation? Your data is held in the latch. Your data is being held in the storage node. So whatever data is there over here, it will keep on keeping the data as it is. So let's assume initially, let's assume that the 0 is stored in storage node Q. Okay, so node Q is storing 0. Agree? So QB node will be storing 1. So this is storing 0 and this is storing 1. QB node is storing Q is storing 0 and QB node is storing 1. Agree now? Because if this is 0, see, listen here. If this is 0, this will be 0. So the output of this will be 1, correct? If this is 1, this is input. So this is input to the first inverter. So the output will be 0. Is this correct or no? Yes or no? So these storage nodes will continue to hold the same data. So voltage at node Q will be storing 0 volts and voltage at node B will be 5 volts. Let's say VDD is 5 volt for example's sake. Yes or no? Now tell me, whenever Q is 0, which transistor is on? Q is 0 means what? Which transistor is on? Come on, tell me. M, sorry? No, Q is 0. Output of inverter number 1 is 0. 0 means which transistor is on? M1, right? And M3 is off. Yes or no? Acha, let's consider this. This is 1, right? This is logic number 1. So if this is 1, M3 will be off and M1 will be on. Does you agree? Yes or no? So in this case, if there is a 0 over here, M1 will be on, M3 will be off. Agree? And similarly over here, if Q bar or QB is 1, which transistor will be on? If this is 0 now, so M4 will be on, right? And M2 will be off. So here M4 is on and M2 is off. That means when Q is 0, to M1, the transistor NMOS transistor M1 is responsible for holding the data at logic Q, at node Q. Yes or no? So M1, transistor M1 is responsible for holding the data at node Q. And what is that data? Logic 0. Yes or no? Hello? Following? And here if M4 is on, it is responsible again. M4 is responsible for holding the data at node QB, that is logic 1. So it will continue to hold that data. Yes or no? Can it stay? Can the data state change the state now? Can it ever change the state in this scenario? Tell me. To storage node Q में we have 0 stored and QB में 1 stored. Can this data ever change without any external interference? So that's why we call it as a hold state. Yes or no? So the data is held into this memory cell. So Q will remain Q will remain 0. Voltage at node Q will be 0 and voltage at node QB will be logic 1 only throughout. Yes or no? So this is hold state. So we keep on holding the same data throughout. Understood the working in the hold operation in the hold state, everyone? Yes, no, what? Others are able to follow? Yes or no? Okay. Now next. So if I remove VDD over here, let's say if I remove VDD, VDD has removed. So what will happen now? Will the data will change or data will be same? So let's say here it is VDD is removed. So what will happen to this QB? Will it store 1 now? QB will store 1? No. If you remove VDD, your data is lost. How? Because VDD is responsible to charge QB node to logic 1. Now if VDD is not there, who will charge this node to logic number 1? So data will be lost. That's why, so here data will be lost means what? QB will become 0. That means data is changed. If 1 was stored, it is lost. Okay, that's why it's called as a volatile memory. Okay, agree? So without VDD, the data will be lost. Understood this? Okay. Now, this much is clear to you. This is 4 transistor, na? So we are building up on the SRAM 60 SRAM cell. Don't worry. Okay. So the first part I will explain 3 operating modes: hold, write, and read. So if they ask you in the exam, draw the 60 SRAM cell and explain the operation, you have to explain hold, write, and read mode. This is the hold mode. Actually, we are building up on the 60 SRAM cell. Don't worry about it. Yes or no? So can I go next to the next point? Yes, no. Okay. Let me connect my writing pad. Okay, I need to close this. Something is wrong. I'll open it again. Don't worry. What happened over here? Yeah, now it's fine. Now, we have seen the 40 SRAM cell up till now, which is as follows. So we have this transistor. This is inverter number 1. This is ground. This is VDD. Yes or no? And then we have another inverter. This is inverter number 2. Okay. The connections are made in such a manner that the output of first inverter is connected as the this input. Input is connected to the output of second, and the input of second is connected to the output of first. Yes or no? And this data we call it Q. This data node we call it as QB. So, but this is basically, I'm not writing this thing. This is nothing but input to second inverter. Yes or no? And this is nothing but input to first inverter. Okay. Now, if I see the inverter characteristics, VTC curve, this is V out upon V in. Alright. Now, what will be the characteristics? ऐसे होता है ना characteristics everyone? Yeah. And what is the switching threshold? If I have a line V out equal to V in, where output is equal to input. So, this point is called as a trip point. Yes or no? This point is called as a trip point. So, here at the trip point, V in is equal to V out is equal to V in. When to the left hand side of this point, what is my V in and V out relation? Your V out is greater than V in. Yes or no? And on the right hand side of the trip point, I have my V out less than V in. Yes or no? My V in is more, whereas Vn is V out has reduced to 0. So if I just shift this, ideally this should be VDD by 2. Yes or no? So if I change my input, if I am at 2.5 volt, let's say, if VDD is 5 volt. So if I slightly change my input to lower side, automatically my output will become greater than my V in. So output will be very high for low value of input. Okay, and soon as if I change my trip point over here onto the right hand side, my output becomes less than V in. So that means my state of the output changes just by changing this trip point. Yes or no? Agree or no? Hello. So we need to apply, these are storage nodes, right? So these two are storage nodes. They are storing the data. But externally, how do we read the data and how do we write the data? We need to apply external voltage of force at the storage node. So we need to apply external voltage, or we need to force at storage nodes. Okay, and let's say we need to write 1 into this storage node Q. If the data is 0, we need to write 1, or we need to read the data, whatever it is the data at the storage node Q, either it is 0 or 1, we want to read the data. So we need to connect something over here and something over here, and we have seen what we have to apply. So we have to apply what? Two additional transistors or switches. So for applying external voltages at the storage nodes, we need two additional transistors, and these transistors are called as access transistors. What are they called as? Access transistors. Okay, so this will change the voltage of the storage nodes, and then we can write into the memory, read from the memory, do all kind of operation. Right now it is just in the hold operation mode. It's just in the hold mode. Are you getting it what I'm saying, everyone? Yes or no? You understood why we need to apply external voltages over here at Q and QB? Because we want to read from the memory, or read 0, read 1. We can do only 4 operations. We can do read 0 operation, read 1 operation, write 1, or write 0 operation. Okay. So whenever we say all these operations with respect to SRAM memory cell, this is with respect to node Q. So all these are with respect to node Q. Just remember it. So whenever we are read 0, when we say read 0 operation, we are reading 0 at node Q, reading 1 at node Q, writing 1 at node Q, writing 0 at node Q. Are you understanding, everyone? So automatically the QB node will change accordingly, since it's a cross coupled inverter. Is this clear to you before I move ahead, everyone? Yes, no? Hello? Okay. So read 0, read 1, write 0, write 1. These are the 4 operations we need to explain with respect to SRAM cell. And all these operations are with respect to node Q. Now let's draw 60 SRAM cell. Everyone, for the first time we are drawing 60 SRAM cell. So let's draw it together. So these inverters, you draw it as it is. Now you know how to draw them. This is an inverter, this is VDD. Input tied together, this is ground. Similarly, one more inverter over here. Alright, now do the connections. So this wire is connected over here, and this wire is connected over here. You have to connect it properly, okay? This is again VDD. So these are my 2 inverters. Okay, so 4 transistors are done. Now next we go for Excess transistors. So excess transistors are as follows. So we have one excess transistor over here. Excess transistor can be controlled by word line. That means its gate terminal is connected to a word line like this. So this is connected to a word line, WL. WL stands for word line. And to write the data, it has one more control signal, bit line and bit line bar or BLB. Okay, these are two independent control signals. Not related कि BL should be 0 and BLB should be 1. ऐसे नहीं है. BL, there are two control signals, so it can be 0, 0, 0, 1, 1, 0 or 1, 1. So, yeah, let's write down the names. This is node Q, this is node Q, and this is node QB, or we can call it Q bar. Then let's write the name of the transistors. This is M1, M2, M3, M4, and these are excess transistors, M5 and M6. So this is bit line, BL is bit line, BLB is bit line bar or complementary bit line, WL is word line, Q and QB are storage nodes. Okay, let's talk about the transistor M1 and M2. What are M1 and M2 called as? Pull down transistors, because these are NMOS. So these are pull down transistors. What about M3, M4? These are pull up transistors. And what is M5, M6? These are excess transistors. Alright. And we have three control signals. The three control signals are can you tell me what are the three control signals? Bit line, BLB and word line. These are the three control signals. Okay. And we need to explain the operation of a SRAM cell in three modes: hold, read, write. 1, 2, 3. Alright. So I'm writing a table, I'm drawing. Have you drawn this diagram, everyone? Yes or no? So this is my control signals: word line, bit line bar. And here I am writing operations. So we have a hold operation, then we have a read 0, read 1, write 0, write 1. Okay. All of you understood? And we have to write the status of this control signals for these operations. Fine. You have to fill this column. So we'll fill this column as I explain you the operation. So once I explain you the operation, if they ask you in the exam, you can write about the SRAM cell. So that means the operation of SRAM cell is complete. Have you drawn this, everyone? Okay, everyone ready now? Hello, can you all reply? Okay, fine. So now we will be writing 0 on the storage nodes. So let me start. I hope you have completed. So here we draw the SRAM cell again. We are first operation will be write 0 operation. Write 0 on storage node Q. Okay. So for write 0 operation, let me just draw this again quickly. It will be a practice for you. So you have drawn it once, so no need for you all to draw. Let me do it quickly. This is VDD. This is VDD. Connect the output input to the output over here, and connect the input to the output over here. Then we have access transistors over here and over here, and then we have word line which are commonly connected, and here we have bit line and BLB, bit line bar, we whatever we can call it. Okay, fine. Then we can name this transistor M5. This is M1, M2, M3, M4, M6. Okay. Acha, tell me, when I want to write something on the storage node, what are my storage nodes? Q and QB. Okay. Q and QB bar. Yes or no? Now, if I want to write something on the storage node, I need to apply from external voltage, right? So, what should be my word line? Should my access transistors be on? Yes or no? Hello? Should I access transistors be on? Should M5 and M6 should be on for write operation? Yes, of course. For read and write, access transistors should be on. So let's assume initially uh, we are writing logic 0, right? So let's say node Q is storing logic 1. So obviously QB will store logic 0. Let's assume this initially. Okay. For this to happen, what should be my word line now to initiate the signal? Word line should be 1. If word line is 1, M5 and M6 are on. Agree? Third, what should be my bit line? If this is 1 now, अगर ये मेरा 1 है अभी, right now this is 1, this is 1, this is 0. So tell me, what should be bit line and what should be BLB? Come on. Hello students, kindly reply. ये 1 है. I want to write a 0 into it. So that means what? This is a pass transistor na M5. When can I write a 0 into it? Students, come on, tell, the time is leaving. I have an exam duty. You all are listening? So please inform me. I mean, you cannot stay mum. Yeah. Tell me what should be BL. So that my node voltage Q changes from 1 to 0. Yes. See, one more thing I have not told you. These bit lines have parasitic capacitances like this. So this bit line, this is called as CBL, and there is a parasitic capacitance, large parasitic capacitance present. This is called as CBLB. All right. Okay. You make the connections like this. So now what will happen is, if bit line is 0, what will happen? How? Bit line is 0. So what will happen is, this M1 and initially, yeah, M1 and M5 will be discharging slowly towards ground. Okay, obviously if this is 1, this is 0, so bit line will be 1, here this will be 1. All right, so this capacitor will charge. Okay, so what will happen is, let me explain. So your CLB, your bit line should be 0. Okay, and word line should be 1, obviously. So your CBL discharges. Okay, CBL discharges via M1 and M5 like this. So this node voltage will discharge now. Discharge via this transistor. Okay, so when it discharges, it changes to 0. The new voltage is 0 over here stored. When this charges entirely become discharged to 0. Now this is 1. So it will start charging. So who will charge? It will charging towards M6. So it starts charging. So QB will be storing, instead of 0, now 1. So my state has changed. I have written a 0 instead of a 1 on storage node Q. So this is how I write 0 into storage node. Okay. So what should be my signal for write 0? Word line should be 1. Actually word line should be 1 for all operations. Except for hold. Hold operation ke liye word line should be, we'll see that in few thing. We are into write 0. So bit line should be 0 and bit line bar should be 1. This is the state. This is explained over here. Okay, so bit line should be 0 because we want to pass 0. And your M1 and M5 discharges via this transistor. So uh, this charge stored in Q will be becoming Q. 1 will be becoming 0. So that's how we can write a 0 onto storage node Q. Agree? Everyone? Now can we go for write 1 operation? Yes or no? Okay. So next we go for a write 1 operation on storage node Q. Okay. Can I explain it here? I mean, let me draw it. No problem. What happened? Someone is replying in the meeting. Can you tell me orally what happened? Here it is. And this goes over here. Then we have two access transistors. One over here. One over here. Both are word lines. And this is bit line. This is bit line bar. Okay. And we have a capacitor connected to the node. See bit line and bit line bar. Okay. So now CBL discharges via M1 and M5, and here BLB charges via M6 to VDD. So that is what happens actually. Okay, over here. So initially we assume here, let's say we want to write 1. So let's say this q and this is q bar. So let's say it is storing 0 now. So initially it's storing q में 0 and q bar में 1. Now what will happen? So initially we can say q is 0, qb is 1. So here we can say hence q becomes 0, qb becomes 1. So here tell me, word line should be activated, yes or no? So word line activated means M5 and M6 are on. So this is M5, M6 are on. Now tell me what will happen. This is 0, right? So this will be 1. This is 1. So this is 1. So tell me now what will happen. Oh, sorry. One thing I missed out. See, here if this is 1, if this in the earlier state, if q is 1, that means this is 0. This is 0 means M3 is on. Sorry, I missed out on this. So M3, which was storing 1, now it will discharge. So via this, ये देखो ऐसे discharge होगा. Sorry, I forgot. So Q was charged to VDD via M3. So now M5 is on. So it will bring down this voltage level to 0. Okay, sorry for that. And in this case, your input is what? 1. So M2 is on. So then it will charge up till this voltage will go up till VDD. That is what will happen. In this case, which transistor is on? If you apply 1 over here and 0 over here, tell me. If you apply 1 over here, this transistor is on, right? M1 becomes on. This is M3. This is M4. This is M2. Okay, so tell me which transistor is on? M1 is on. Yes or no? Hello? M1 is on, na? If Q is 0, if QB is 1, then here M4 is on. So now what will happen? Tell me. What should be my bit line? If I have to write 1 over here, tell me what should be bit line. Bit line should be 1. So this bit line should be 1. Okay. So this bit line will be 1 means what? So capacitor will charge via M5. So CBL charges via M5. So your Q, slowly the voltage at storage node Q will rise and that will become logic 1. So this will become 1 and this will become 0. Because over here what is happening? Your capacitor is discharging, I guess, right? Because this is becoming 0. So it will discharge via this part. See? Like this. So the node voltage QB will fall down and become 0. Here the node voltage will rise. So this capacitor will increase. The CBL will charge via M5 and the node voltage Q will increase to from 0 to 1. And here node voltage QB will fall from 1 to 0. So hence we have written 1 on the storage node. Understood this? So for this what do? We make BL as 1 and BLB as 0. So here BLB is 0 and BL is 1. Understood this? Everyone? Yes or no? Now we are going for read operation. So once we explain read operation, your majority of your task will be over. Now let me explain you read operation. So let's write down. Acha, I haven't explained you hold operation. So hold operation mein what happens? Can you tell me? Hold operation, what should be the status? Here only tell me. So for hold operation, I don't require access transistors. Yes or no? So my word line should be, how to deactivate access transistors? Word line should be 0 or 1. Yes, if word line is 0, these two are off, and these four transistors will keep on holding the data. So irrespective of BL, so BLB and BL should be XX. It can be 0 or 1, it doesn't matter. So for hold operation, the diagram will become this, right? When this will become when the access transistors are not present. So access transistors will be off when W word line will be, control signal will be 0. Agree on this operation? So if they explain you the operation of 60 SRAM cell, you have to draw this table and you have to explain all of this. Okay, M1 and M2 will be responsible for pulling down the voltage at the nodes. M3, M4 will be responsible for pulling up the voltage at the nodes. And M5 and M6 are the access transistors which will provide the data to the cell. That is a read and write status. And we have seen the write 0 on the storage cell which was overriding 1. And we have also seen the write 1 on the storage cell which was overriding 0 to 1. Okay, now we go for read operation. How is read operation different than hold and write operation? Can you tell me? Anyone? Anyone has any idea till the time we draw the diagram? So read के लिए already the data should be present. The data should be present in the memory cell, right? In the storage cell. Yes or no? So here this is going over here and this is going over here. Then we have access transistors. Alright. This is word line and this is bit line. BLB. And remember we have a capacitance present. CBL CBLB. Okay. So we will be studying about read 0 operation first. Agree? This is M5, M6, M3, M4, M1, M2. So first we are talking about storage node Q and QB. Let's say 0 is stored over here. So here it will be 1, right? Okay. Now tell me how this will operate. So for reading the data from the storage cell, reading 0, let's go for read 0 operation. So we'll be reading 0 or reading data 0 from the storage node node Q. Okay. So we will see read 0 at storage node Q. Okay. So first we will assume Q is 0, Q is storing 0 and QB is storing 1. Okay. And secondly, of course, we have to turn on the word line. So word line is 1 over here. That will turn on my two transistors M6 and M5. So these both transistors are on. Okay, M6 and M5 are on. So that we can access the data. Now, one more important condition is there. What is the condition? Third condition is there that this transistors, parasitic capacitors should be pre-charged to VDD. This bit line should be pre-charged to VDD. So CC, CBL and CBLB must be pre-charged to logic 1. So how can we pre-charge something to logic 1? Can you tell me? That means what? BL and BLB both should be logic 1, right? So you will say, sir, it is BL bar. No, these are independent signals. It's not that this is BL, so this is BL bar. It will only take complementary signals. No, not at all, because not at all related to inverter. These are independent signals. So BL and BLB can take 0, 0, 0, 1, 1, 0, 1, 1. Understood? So in this case, if both should be precharged to logic 1, that means BL and BLB should be 1. Both 1, 1. And word line should be 1. Okay? So that means in the table, whether it's a read 0 or read 1, all this should be 1, 1. Please update the table. Table updated. Now let me come to read 0 operation. So now, what is the status over here? Right now the status is word line is logic 1. So M6 and M5 are on. Bit line is also logic 1. So these both are 1 now. Now tell me what will happen. So if it is 0 over here, come on, be interactive please. If it is Q is 0, if Q is 0, what will happen? Node Q, storage node Q is storing 0. So what will happen? Tell me. Which transistor over here, M3 or M1 will be on? Come on. Word line is 1 means these two transistors are on. That is for sure. Now if Q is 0, which transistor is on? M3 or M1? Sorry? M1 na? M1 is on. Okay, so this is on, which I'm marking in yellow color. M3 is off, right? Yes or no? Now, if QB is 1, which transistors are on? M4, right? It's a pull up, na? So M4 will pull it up. So M4 is on and M2 will be off. Agree or no? So this is on. This is on and this is on. Whereas M2 and M3 are off. Agree or no? Yes? Yeah. Now, if you see, now, what is the potential difference between the bit line and Q now? What is the potential difference over here? So let me draw this section again. I have a word line which is 1. I have a signal over here. Potentially, if this is 1, right? So this is logic 1. So M1 is there. This is M1. This is M5. And bit line is this is the situation now. Yes or no? So these two transistors are on. These are NMOS transistors. And Q was storing 0. So what will happen now? Tell me. Hello. Will this voltage at Q reduce or increase, or what will happen over here? So there is a potential difference. Now, do you agree? This is bit line, right? This is 1. So is there a potential difference between bit line and Q? Yes. There is a potential difference. So what will happen is your capacitor CBL will try to discharge now. Will try to discharge via, it was storing 1, now it is pre-charge, right? So let me tell you how to pre-charge. Do you know this logic, pseudo NMOS logic? ये पता है ना आपको? ये पता है ना pseudo NMOS logic? So we apply pseudo NMOS transistor over here. So this is what is keeping the bit line high during the read operation. Okay, so these are the pseudo NMOS transistors. Okay, so this will keep the pre-charge BL and BLB 1. Now both are 1. Now this is the difference, voltage difference between BL and Q. So what will happen is this charge is stored. So CL is initially pre-charged to VDD. So now it will decrease and go to 0. Yes or no? So that means voltage, agree? So your CC will discharge slightly via M5 and M1 because both are on. Yes or no? So CBL will discharge via these two transistors like this, as I have shown over here. Similarly, over here, what will happen over here? This is 1. So here we can say uh, voltage at BL. So this voltage was VDD, it will reduce slightly. So it will be less than VDD. So it was holding what? VDD, right? Initially it was holding VDD. Now it has reduced slightly because it is discharging slightly. Okay, why slightly? Why it is not completely discharging? Because here it is 0 already and here it is 1. So it will continue to discharge slowly because we have M5 transistors, excess transistors also present over here. Okay, so this bit line will be VDD. Was VDD, now it has reduced slightly. What about bit line BLB voltage? So voltage at BLB node and voltage at QB. What is the difference between them? They are same, almost same. So this capacitor will hold the charge. So CBLB will hold the charge because there is no potential voltage difference between QB and BLB line. Okay, so what will happen is voltage at BLB will be equal to VDD. Yes or no? That means now voltage at BL is reducing slightly and voltage at BLB is 0. Yes or no? Now we have to do one more thing. We have to connect the sense amplifier. So what is a sense amplifier? We take this line over here. We take this line over here and we connect it to sense amplifier. So what does the sense amplifier do? This is voltage at BL. This is voltage at BLB. And it will give the data output. Okay, so sense amplifier will do two things. If it will sense the BL voltage and BLB voltage, if both are same, its output will be, it will give the output appropriately 0. That means, right? So now if BLB here, which voltage is higher than the other? Tell me. If BL voltage at bit line is less than bit line bar, then it will give the output as logic 0. So your data output will be logic 0. And if BL voltage at BL is greater than BLB, then the data output will be logic 1. Now tell me which is higher. BLB is higher, na? So data output will be logic 0. So as you can see, the data output logic 0 is been read at the output of sense amplifier. And what was at Q? Node Q? 0. So this is how you read the data. So read 0 operation is performed. So if the output of the sense amplifier is reading 0 and the data stored is 0, we have read 0 in the memory cell. Did you understand this operation? Yes or no? Hello? I don't know how much you have followed, but have you understood this? Yes? Very good. So now similarly you will explain read one operation. So read one operation, I will be just explaining it over here. So read one, exactly opposite will happen. We have to read one at the storage node. So please listen carefully. I'll be only marking with what color I have not used so far. This pink color. Okay. So for reads one operation, we'll assume Q is holding 1 and QB is holding 0. Okay. So this is holding 1 and this is holding 0. Okay. Both word lines are 1. So M5 and M6 are on. Okay. If Q is 1, which transistor will be on? M3 will be on. Okay. And if QB is 0, M2 will be on. Agree? Yes or no? Are come on, tell me. And bitline bar are both 1. All are 1 only. So now tell me, what is the difference over here? Here it is 0, right? And here it is 1. So there is a voltage difference between here and here, right? So what will happen due to that? This capacitor will try to discharge via M6 and M2. Okay, so voltage at BLB will reduce slightly because there is a voltage difference between BLB and QB. Agree? Similarly, over here, M3 is on. Okay, and here the voltage level is 1, and here also it is 1. So there is no voltage difference between Q and BL. So what will do? What will capacitor do? Capacitor BL will retain the charge, will retain VDD level. That means voltage at BL will remain VDD, whereas voltage at BLV will fall down. Okay, so here it is almost VDD, and here it is less than VDD. Okay, so what will be the output now? Tell me. Here BL is greater than BLB. So what will be the output? Data output. Nahin, logic 1 na. See, BL is greater than BLB, logic 1. So initially it was Q was storing logic 1. Okay, and now the sense amplifier is reading logic 1. So we have read 1 from the memory cell. Agree? Understood or no? So this completes the operation of 60 SRAM cell. So in the exam, if they ask you explain the operation of 60 SRAM cell, you have to start your answer from here. Okay, then explain the hold mode. Hold mode, you can go over here and explain that how the data gets holded. Here I've explained it very clearly. Okay, then draw this observation, draw this table with the control signals and the read 0, read 1, write 0, write 1 operation, and you have to explain it this way: write 0, write 1. You can explain 1 and write similarly. So you can explain read 0 and write similarly, read 1 operation is carried out. Okay, and you can show that sense amplifier is there, which will sense both the inputs BL and BLB bar, and it will give the output accordingly. Understood? So this completes the operation of 60 SRAM cell. Okay, so now those who want to leave can leave because this is completed. I've explained you what is 60 SRAM cell. Then the difference between SRAM and DRAM I've already covered. Okay, row decoder is covered in the last session. Column decoder is covered in the last session. Now I will cover design strategy and read-write circuits. So these are separate topics. Those who want to remain. Those who want to leave can leave. So I have a exam duty at 2 p.m. So can I continue in around some break time because I want to have my lunch. So like half an hour from now, can I cover it? So I will cover design strategy and read-write circuits then. Is it okay? Hello? So that you also will get some time. So you study this. I will sharing this PDF very soon. So see, this PDF is blank. Now the moment I write into it, then it becomes useful for you, right? So whatever I've written over here, you can write similarly in your exams also. Alright, so all these things are blank now. Alright, so I will fill it up once I complete this and give it to you. So at least anything asked from SRAM, you can answer this. So for the, I'll start the lecture at around 12:45. So from 12:45, so we have covered this from 11:10 to 12:20 or so. Okay, so we'll start at 12:45 and we'll complete till 1:30. Design strategy and read-write circuits. Okay, so we'll resume at 12:45 now. So join back at around 12:45. I'll explain the design strategy for SRAM and read-write circuits for SRAM cell. Okay. Yes. Okay. I'll open the syllabus. Wait. Yeah, you can let me just